The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, and welcome to this session. My name is Andrea Manara from the ITU, the International Telecommunication Union. It is an honor for me to introduce the first of 5 final events for this second edition of the ITU GeoAI Challenge. This challenge aims to provide a platform for collaboratively addressing real-world geospatial problems by applying artificial intelligence, machine learning to advance the United Nations Sustainable Development Goals. Participation is open to any individual from one of the 193 member states of the ITU. ITU also provides a state-of-the-art, free-of-charge compute platform to participants of the challenge which do not have adequate access to computing resources in their respective institution. Today's session deals with the air pollution susceptibility mapping competition. We had 207 participants enrolled in the competition, and 35 active participants submitted solutions on the ZINDI platform. The top 3 teams were invited for today's session to showcase their solution, and they will be awarded during this session as recognition for their outstanding performance. The goal of this competition was to use machine learning to produce air pollution susceptibility maps at the city level with 5 meters spatial resolution in order to support decision making for improving the resiliency of the city. This challenge is curated by the GeoLab from Politecnico di Milano and contributes to the United Nations Sustainable Development Goals 11 and 13, which focus on creating sustainable and resilient cities and combating climate change effects, respectively. Now it is really my pleasure to introduce the host of this problem statement. Angeli, if you can switch on your camera. Hello. Angeli is a PhD student in environmental engineering at Politecnico di Milano, working on machine learning applied to hazard susceptibility mapping, and she's also a WebGIS consultant and the World Bank. I would also invite Maria Brovelli is professor of GIS and the Copernicus Green Revolution for Sustainable Development at Politecnico di Milano. And she's a member of the School of Doctoral Studies in Data Science at Roma La Sapienza University. She is also the coordinator of the Copernicus Academia Network for the Politecnico di Milano and the head of the GeoLab, which is the interdepartmental lab to which 7 departments of Politecnico di Milano are contributing. Amongst her many other duties, she's the chair of the UN GGIM, the Global Geospatial Information Management Academic Network. She's a curator of the Geospatial series at the AI for Good, organized by the ITU in partnership with the 4th UN Sister Agency. And Maria is also indeed the leading person behind all the GeoAI activities at the ITU, including the efforts focused to building up a syllabi for GeoAI and the body of knowledge. I will now give the floor to Anjali for her introduction to the competition, and afterwards we will have 10-minute presentations for each of the selected competitors. Anjali, the floor is yours.
Thank you, Andrea. Let me share my screen. Okay, good morning, everyone. This is the GeoAI Challenge for Air Pollution Susceptibility Mapping in Milan. As you know already, my name is Anjali, and I'm a PhD candidate in environmental engineering at Politecnico di Milano. This challenge was uploaded in the Cindy Africa platform, and it is with the aim of producing seasonal air quality index susceptibility maps in Milan. This was proposed by Politecnico di Milano, specifically by the GeoLab, the Geomatics and Earth Observation Lab, where you can find the QR code here in the slides if you want to check out more information and to check the other projects that we are involved in. And then, well, there is me. So about the challenge, in fact, this comes from the fact that Milan is an air pollution hotspot due to its surrounding components. Milan is located in the Po Valley, and the surrounding topographical components contribute to low wind circulation, which enhances the accumulation of pollutants in the air. So here you have an example of this of the pollutants and the location of the city of Milan in Italy. So the objective of this challenge is to produce air pollution susceptibility maps. And as mentioned before, it contributes to the Sustainable Development Goals 11 and 13, specifically on the making cities and human settlements more resilient and to work towards the impacts of climate change. Here we have an example. In the meantime, later I will talk to you about the challenge in detail, but here you have an example of the air quality index that actually is a classification on to give us insights about the quality of our air. And here we have the different classes. And this is a map where Milan is around here. And we can see this is a map of June of this present year, which shows how the air quality index goes from poor in some hotspots to moderate and fair towards the mountains. So the data models, how to produce this air quality index, you gotta have the concentrations of the pollutants, which are classified into single classes. And then the worst class from this single pollutant classification is taken as a general air quality index. So as for this, time series data was provided for pollutants and for meteorological variables. Here you can see in the map on the left the locations of the in situ stations from the ARPA Lombardia network. ARPA is the local environmental agency, which is openly providing all this data. And in the yellow asterisks, you can see the locations of the meteorological stations, and in blue dots, you can see the locations of the air pollution stations. All these time series data from 2016 to 2022 were provided to the participants alongside static data regarding digital terrain models that cover population density, road, railways, and underground networks, and so on, other variables. Participants were also encouraged to use other data, as this was only in situ data, other open data providing air pollution or other relevant information could be retrieved from the Copernicus sources on the other ones. So this was highly encouraged. And to keep in mind, all the data is open, all the data that we are providing, and so should be the additional data used by participants. And for sure, all the approaches must be reproducible, publicly available, and the code was limited to Python. Then we have the evaluation and prices. Evaluation consists of CSV files containing the model predictions, and then from that the leaderboard was constructed to see which were the top participants. They developed model code, a report containing all the solutions, their models, and comments and information regarding the decisions that they made and the approaches that they took to solve this problem, and while participating into the current meeting. Well, after evaluating this, the report and the best model have a specific weight. The report has 40% and the model scored 60%. And here are the prices for the first, second, and third places. So that is all from the remarks on the introduction about this challenge. Thank you, and let me know if you have any questions. And here is my email in case you want to contact me afterwards. Thank you.
Okay, so thank you, Angeli, for the nice presentation of the problem of the topic. And now is the time for our candidates. So let us see the solutions that they proposed for the problem you posed. I suggest to start in the alphabetical order. So we can start with Isaac. Good morning, Isaac.
Hello, good morning.
Good
to
morning. If you
everyone.
want, while you are sharing your presentation, if you want to very quickly introduce yourself.
Okay, thank you very much for the opportunity. I believe my screen is being shared now.
Yeah, it
Is my
is.
screen visible? Yeah, thank you very
Yes.
much. So, yeah, I'm presenting on my solution for the air pollution susceptibility mapping. So I'm Isaac Oluwafemi Oguni, as you wanted to know a little bit more about me. I had my undergraduate studies in aerospace engineering. Yeah, and then so how did I get into data science? I got into data science through a fellowship, that is an AI fellowship with Blossom Academy that was sponsored by GIZ. I'm currently a top 1% data scientist on Zindi. Yeah, so that is a little bit about me. I hope that suffices.
Yeah, thank you.
So I can go ahead with my presentation.
Yes, please go ahead with your presentation.
Okay. Thank you very much. So we first had to look at certain trends in the data. Okay, so just as the introduction was made, the data consisted of inputs from 2016 to 2022, but the issue is that the 2022 was used as a final data, final test data. So we do not have it, inculcated, or we don't have it captured here. Okay, so when you look at the data, you realize that an AQI rating of 2 dominates spring and then summertime. Okay, so that is this line you see over here. So in both summer and then spring, you see that AQI of 2. And I think AQI of 2 is fair air pollution. Like the air is quite, the air quality is quite fair. Okay, so that is what was understood from analyzing the data initially. Going on further in winter, the air quality is generally low. That is around 4. But we see that getting from 2020 to 2021, the air pollution or the air quality is increasing a bit. Okay, so that is air quality of 2 is increasing. Okay, you can see it from this line. It's increasing to the side, whilst the poor air quality is reducing. So the number of occurrences or observations of poor air quality is reducing gradually, whilst air quality index of 2 is increasing. So that is it with the initial analysis. So after finishing with the initial analysis, how do we approach the problem of mapping the air pollution susceptibility of a particular area? Okay, so we approach it as a forecasting issue. Okay, so forecasting and then classification. Yeah, so you forecast which class a particular area will fall into. To go about it, we first looked at each of the locations and then we map their previous years. Okay, we set their previous years values. So for instance, if there's a location as location A, what was its value? What was it AQI rating in 2016, 2017, 2018, 2019, 2020? So we look at those things and then you try to fit a model to learn from the various indications, the various features of the various years, and then use it to predict a current year. So for this particular model, we use only a one step. So we look at just the previous year, not maybe 3 previous years, because we had limited number of years. So that was I think from 2016 to 2021. Okay, so we limited it to just 1 year. So you look at the previous year and use it to predict the next year or the present year. So last year will be used to predict this year. So that was the approach. And then the model architecture was basically a randomized set CV object. So we use a randomized set CV object because we want to produce a model that will be generalizable. Okay, so not based on any statistically insignificant occurrence. So you want to as in try it multiple times and then see that this is something that can be trusted. So that is why we use a randomized search CV. So it's a cross validation. It searches and then finds optimal parameters, and then it's a pipeline. So for each data it receives, it scales the data to approximately the same ranges. Okay, so the same range, so that the machine learning algorithm will assign meaningful weights, not just be biased based on the magnitude of the values in each feature. And then we move on to selecting the keyword. So we have a number of features, but then not every feature is very valuable in predicting the AQI rating of a particular location at a particular time. So what do we do then? We get this select keywords to select a number of features that will be very important in predicting the AQI rating of a particular region. Yeah. So and then the last step is to use a random forest classifier. So a random forest classifier that was chosen as a result of experimentation. Okay. Yeah, it was chosen as a result of experimentation. So moving on, we come to model evaluation. So how do we experiment and then get random forest classifier as a best model to use for this particular problem? So we ran for different models. So as you can see from here, we ran from 11 different models. So based on running for the 11 different models, please put it in mind that these strange scores are randomized CV scores. Then the final labelable score you see here is not a cross validation score. It's just for a single data point or single run score. So that was 99.1. But then for the randomized search CV, okay, we got a 98.5% accuracy. Okay, and then it translated into a test accuracy of 97.6. How do we have train and then test here? In order to be able to properly evaluate the model, we have to break the data we have into train and then test so that we can better understand the performance of the model even before we come on to the final test. Yeah, so we have to validate our models locally. So that is how come we choose random forest classifier as the algorithm to predict AQI rating. Moving on, the conclusion here, we found out that the model is very good. It's very good. It predicts with 99.11 accuracy on the final test data that was used by Zindi2 as a private leaderboard score. Yeah. So what are the 10 most important features that help in predicting the AQI rating of a particular region? So what we see over here is the PM25 AQI. So that is for the previous year, PM25 for the previous year. So this is in a descending order of feature importance. So and then we think about suggestions. So how can we better improve this model? The way in which we can better improve this model is to think about increasing the data available. Okay, so you can think about getting more years data. That is one way. But what we suggest over here is also to consider using intra-year data to predict for future for AQI within the same data. So for instance, you can use AQI data of August to predict AQI in September. Okay, so instead of just using it on a yearly basis, we are restricted. Okay, the amount of data restricted us to do it yearly, but then we can approach it in a way that will take advantage of AQI ratings within a particular year to predict AQI ratings within the same year, but then just a few months ahead. Yeah, so that is basically the whole overview of this submission. Thank you.
Okay, so thank you so much, Isaac, for your very nice presentation and for accepting this challenge. And we will see in the end of the result. The presentation was very good. I want to congratulate with you. And now we go to the second one. So the second one is Julius. So Julius, okay, now we have Julius. So Julius, please introduce quickly yourself and then let's go to your presentation.
Thank you very much for this opportunity. Indeed, I'm very glad that I got to reach at this point, and thanks to ITU, thanks to the host of the competition. Yes, so I'm going right away to start my presentations today. So my name is Julius, and I'm a graduate student here in Kenya, and I'm pursuing a master's degree in data analytics. Currently, I work in the financial markets, mostly research, and my interests are time series problem statements, other observation problem statements. Currently, I'm ranked 14 out of over 70,000 data scientists on Zindi platform. Yeah, so that is basically Julius. So I hope that's enough. So agenda of the day. I will start with the introduction, move to data analysis, and then my proposed solution, the results, and then do a conclusion and improvements that can be done. So I think this one was well done by the host, so I might not spend a lot of time here in the introduction, but she already mentioned that in Milan City, there is that unique air quality challenge due to the geographical features, the Alps and the Apennines. They make air circulation a real problem in the Po Valley where Milan City is situated, leading to air pollutant accumulation. So, so the concerns is that air pollution involves definitely hazardous chemicals in the atmosphere, posing health risks to citizens. So pollution is normally assessed using an air quality index, providing a comprehensive view of the overall pollution landscape. So that index, that air quality index, is actually what you are trying to model or predict in this challenge. So the project focus was to utilize machine learning models to create city level air pollution susceptibility maps with a 5-meter spatial resolution. So this one will help in decision making and also enhance city resilience against environment challenges. So I move to the next. Sorry. As shown in the map there, we were given some train data from the metropolitan city. The red boundaries in my map there, you can all see it. So I can probably use a highlight. Okay. Yeah. Just a minute. Yeah. So the boundaries, the red boundaries show the metropolitan area of Italy, and then inside that metropolitan, we can all see the meteorological stations in the red dots or the yellow, the orange dots. Then we can also see the pollution station. These are also the in situ stations. The pollution station, they are the blue dots. So for the train data, there was enough these in situ stations to track air pollution and other meteorological factors, and therefore the data set was provided. But for the test data set, we were not given because we wanted to model the Milan city, the blue boundary. And you can see inside there isn't enough probably in situ stations, that is pollution station and meteorological stations, to track air pollution levels. So we were left to be creative on how we came up with the test data set. Yeah, so additional data sets were provided for year 2022, as shown in the yellow on this other map here. So these were interpolated grid data provided as extra data. Yeah, so and then another addition, topographic data for Milan commune was also provided. So the approach was to take the seasonal interpolated data, the one we show in yellow, and then merge. First of all, they were given in seasons, 4 seasons. So I concatenated all of them to form that one being seasonal interpolated data for 2022. Then I also merged now that this data with the given topographic data for Milan. I merged to come up with that data, and then use this to interpolate the test or to build the test data for year 2022. So that was how I approached the problem. The train data definitely was given from 2016 to 2021. Yeah. So now with this test data and train data, I had about 48 features now in total, after creating some few additional features. So I did some feature engineering. So but not much, but I just did some location-based information, tried to create the season in train data set, and then try some rotational features where we just rotate the latitude and the longitude by 45 degrees and 30 degrees, just to see whether the model will be able to benefit from that. So after that, I trained a 5-fold light GBM classifier, and then you found the test, and then you get your predicted air quality index. So the results, so I first tried 4 tree models, the XGBoost, Light GBM, acoustic gradient boosting, cut boost, the 4 of them. And then I tried to track the time, the train time, and also the inference time, as well as the accuracy, definitely. So just to note that I used default settings for each. So something to note. And then the accuracy from cross validation for XGBoost was the top at around 0.77. But when I uploaded to Zindi, my predicted AIQ for test data set. The best model was like GBM. And actually, it was also the best in terms of training time. Took around 31 seconds to train, to train. And then to infer the best was CatBoost at around 2.5, but also like GBM average around the same. Okay, so I tried some few things. I tried to remove the season feature from the data set and see how the models performed. And without the season features, the results remained dismal, as you can see here. They would do very well on the local machine. They would average around 0.6. But when you upload on the private leaderboard, they would really perform very poorly without the season feature. So I found that out. I also tried out, what if I only use season feature? I do away with all the other features and just try to use season to forecast the AQ numbers. And what I found is that the season feature alone gave a great score already, but not in the cross validation, not in the during training. During training, all the four models they had a 0.5836 accuracy, but then you upload to Zindi, again they would get a 0.99 accuracy, which was quite high. So there is that big deviation between train and the leaderboard. So I settled on light GBM model because it showed superior results already. And then I tried one last thing. I tried to do more exploration with features. So I broke down my features into categories where I used latitude, longitude, and season alone. And this one gave me a very good results on the leaderboard, but not on the train. Then I tried meteorological data, such as maybe temperature and such. On the machine, about 0.63. When you upload on the leaderboard, 0.4, just it underperformed, in short. Yeah, and that trend was observed for the other categories. The geospatial topographic data, again, just average. The land cover map data, again, they performed averagely. And also the geological map data, again, average. Yeah, so for the engineered features, the three categories, they would perform also like latitude, longitude, and season alone, just because they were engineered from the same features. So they also performed very well there. Yeah, so I tried using all the features, the 48 features that I ended up with finally, and the accuracy was 0.73, while on the public leaderboard it was around 0.85, and on the private 0.82. Then I tried to do some visualization and try to see those features that were showing that shift in they shifted from the train and the test. So I tried to now drop them and just select 40 features using visualization, what I saw from the visualization. And definitely that boosted my performance slightly from 0.82 on the private to around 0.83 accuracy. So that is basically it. So my proposed model was light GBM, and I tried some few things to see how it would perform.
1 minute, Julius.
Thank you so much. Let me conclude. So in conclusion, season was a very important feature. Light GBM ranks the season feature as the fifth most important, while in other models, the season feature dominates as the most influential. Light GBM outperforms other models with the highest accuracy of 83, that's what we saw, and also shortest training time of 1 second. Ensembling results using mode still fall short of light GBM. So even ensembling the four models results, it will not still beat the light GBM one model. So absence of real meteorological station data in the test set used, replaced by interpolated data, may contribute to the disparity in the train versus leaderboard results. So the impact of feature selection on performance also 83 increased from 82 to around 83. So improvements, I think we can try averaging AQ from other pollutants instead of just predicting AQ. Just predict the other pollutants and try to average their values. Apply time series model, like like what Isaac did, use the previous year, 2021, to predict the current year. Use other open source data set. And that's all from my side. Thank you for listening.
Thank you. Thank you, Julius. Another brilliant presentation. So congratulations also to you, to the work you did and the presentation as well. Very accurate, very detailed. So thank you so much. Thank you so much also for this presentation. And now let's see the third one. So what is presenting Xiao? Xiao, the turn is yours now. Okay, I give you the floor before you introduce very quickly yourself and then the solution you are proposing.
Okay, can you please confirm that you can see?
Yes, we can see. Yes.
Okay, perfect. So, hello everyone. Thanks for giving me the opportunity to present it here. Start. Okay. Yeah, so my name is Xiao. I obtained my PhD degree last year from Universitat Politécnica de Catalunya in Spain. So I work in the GNSS industry, which means Global Navigation Satellite System. And currently I work as a software engineer in research and development, also about GNSS. So my main interest is in aerospace, artificial intelligence, and Internet of Things. So also this is the first time I attend any online competition. So actually I came across this competition through the AI for Good Global Summit. I would recommend anyone who is interested also to participate. And the given information are including the following: basically the coordinates, the date, and also some additional data, including the meteorological and digital terrain model data. So about the data being given to us, the meteorological data is given for each season separately. And the digital terrain data was given at 100 meter times 100 meter grid. So for each grid point, there is a data set. And regarding the training data, it contains the records of the above two mentioned data set at different locations and for different dates. And the test data, it's only the coordinates and the season. So that's what we want to predict. So, so here is a brief presentation of the training data. So I plotted how the AQI index, the air quality index look like for the 4 different seasons. So I have chosen 4 different days for each, so 1 day for each season. And here you can see the darker the color, the lower the index. As you can see, seems that season 2 and 3 are generally lower than season 1 and 4. So basically in summer, seems the air quality is better. Sorry, the air quality index is lower. Yeah, so I did some simple data analysis because the given test data is only the coordinates and the season. So we need to bind this data with the given meteorological and the terrain data in order to have all the features. So this is a simple script to bind them based on the geodetic distance to the grid point given in this data set. So after combining these data sets, we have a total number of 60 features. Although among all these 60 features, not all of them should be used. So for example, there are some individual AQI index. I would consider them more as an output instead of input feature. Anyway, so this is some simple data processing. So the proposed methods and the results are given here. So first of all, I have tried just using some minimal features, including just the latitude, longitude, and season. And I used 3 different methods. So surprisingly, the naive Bayes method already achieved 99.1% accuracy, which is seems quite good result. I don't know if it's lucky or unlucky, because this makes the following analysis seems a little bit unnecessary, but still I tried to do some further analysis, including other features also. But when I apply these features, seems the results got even worse. And also for the neural network processing, it was taking quite a lot of time. So in the end, I just didn't put it here. So just some simple conclusions and the future improvement. So as you can see, with a simple naive Bayes model, we already got a very good result. So if we really trust the data, I think that we should actually work a bit more on, for example, the geographically weighted regression models, because it seems that the coordinates is really playing a very important role. But I guess that's the purpose of this competition, to just rely on the data. So of course there are some other features that we can dig into, but that is why we need to do some further exploration in this. Yeah, it's and that's all from my side. It's quite a simple investigation, but this is just my first competition. So yeah, thank you.
Thank you, Xiao. And yes, the geospatial regression was something that we had in mind for this kind of problem. But thank you. Your presentation was very clear. And thank you for sharing with us the result of your analysis and also your enthusiasm. We understand that this is your first challenge, but we hope that it's not your last challenge, because AI for Good is going to propose challenges also in the next years. Okay, but after saying that, now it is the time for Anjali for explaining us who is the winner and the second winner, the third one, because we have 3 winners, correct, Anjali? And so
Yes.
for explaining us what the commission decided. So now it's your turn, Anjali.
Thank you, Maria. Okay, first I would like to thank all the participants for their proposed approaches. They were quite clear. Thank you very much.
Sorry, Anjali, can I ask the 3 participants if they want to switch on their camera in such a way that we can see them? Xiao is here, Julius, and Isaac. So congratulations again, and then let's start again with Anjali.
Yes, of course. Well, for all of you are winners, because there are 3 winners, so and 3 participants who are presenting today their approaches. Thanks for your solutions. They were quite good. The presentations were very well done. And I would just like to point out that it was very important for us that most of the variables were used, because using only latitude and longitude, though giving a very good result, where it wasn't considering the whole phenomena per se. So that being said, also the code and the output of the model, but all the code you presented, being the feature selection, all the data analysis that you did in order to decide which model and which features to use, and then the report that you presented played also an important role on the decision. So the participant who obtained the third place is Xiao. Congratulations, Xiao.
Thank you. Thank you very much.
Thank you, Xiao, for your solution. The participant who obtained the second...
Sorry,
yes.
Probably Andrea wants to share the certificate as well, because I imagine that Xiao wants to see certificate.
Yes,
yes, that would be a great honor.
Let me share the certificate, and then you will also, of course, receive the money prize. So, do you see?
Yeah.
Oh, no, it was visible before, Andrea.
Yeah, fortunately I have an issue with my PC. Okay, so you see the certificate?
Yes.
We do.
Yes.
Excellent.
Wow.
So,
Okay.
third place.
Thank
Well
you.
done.
Yes. Congratulations. Okay, so the participant who obtained the second place is Isaac. Congratulations, Isaac. And of course, now we know that the participant who obtained the first place was Julius. Congratulations, Julius, on your solution. Thanks and congratulations again to all the participants.
Thank you so much.
Yes, if I may add one point where we're not completely happy is about the documentation. So this is a recommendation also for the participants next time, because the solution can be the best one, but then it is very important for these challenges also for the documentation of everything, because we want this challenge to be fair in such a way that means that everyone who wants to repeat what you did can be put in the best condition for repeating it. Correct, Anjali? We want to have a complete documentation. Okay, so, but the solution were good, and thank you so much. And then, Anjali, do we have something else to add?
No, that's all on my side. Just it was enough and good for this first edition of the air pollution challenge. Yeah.
Okay, congratulations again. And now we will give back the word to Andrea.
Thank you very much, Maria, Angeli, and really thank very much to the three winners. It was really an impressive quality of the presentation that you did. Very, very, very impressive. And I also want to thank to all the participants which have enrolled in the competition, but then they didn't submit a solution. So we hope that in the future we will have also more submissions. So I'd like to discuss now a little bit the outlook of the competition, because we will have other 4 finals, 2 this week. So we will have the crop mapping finale that will be tomorrow at 16 Geneva time, and then we will have on Thursday, another finale for another problem, which was always submitted to the GeoLab Politecnico di Milano on the landslide susceptibility. So again, I want to thank Maria really a lot for this very big implication in the competition, and we really hope that the GeoLab had a very good experience with this competition, and then you found some interesting solutions for the work, very important work you are involved with. And then next week we will have other two finale, yeah. One about the location mention recognition, and the other one about the hyperview challenge from the European Space Agency. So it will be very interesting events as well. So please stay in tune. I'd like also to mention we are very much pleased to announce that we have issued a call for papers for a special issue on GeoAI, Geospatial AI, to advance the United Nations Sustainable Development Goals in the ITU Journal on Future and Evolving Technologies. And Maria is the leading guest editor, so I'd like to ask you, Maria, something about this special issue and what are you expecting from that. Let me meanwhile also share the screen so that I can show you the IT website announcing this.
Okay, so thank you first of all, Andrea. Thank you also to AI for Good for the wonderful organization of this event and the support is giving to the organization, to the possibility to these young people to show their activity, to show how good they are, to give them visibility. I mean, the participants, but not only the participants, because I want also to thank Angeli. Angeli was the person proposing the challenge, taking care of the evaluation of the solutions and everything. So it's really a good opportunity for young people. I'm very happy about that. Then specifically about this special issue is a special issue that we decided to give birth because we want in some way to have a place where some relevant papers related to geospatial AI and sustainable development goals can be published. This is completely open for everyone. It is free of charge, so you don't need to pay, but it is reviewed. So it means that the important point is the quality of what you want to propose, and not if you can afford it from the economical point of view. So in the spirit of UN and ITU, this is free of charge, the possibility for everyone for publishing, and for sure there is a big audience because AI for Good, it's a very important summit, events, and so on. And so it's a good opportunity for showing your work, the work you are doing, which has to be related to sustainable development goals and to geospatial AI, because the focus of this special issue is on geospatial AI. So every of you who is interested, please submit to this special issue, and then you will be challenged because there will be reviewers, international reviewers, deciding if your paper can be published as it is, if you need to revise it, and how you need to revise it. This is for everyone, but I hope that young people also will use this opportunity for publishing the activity they are doing with respect to this important topic. And thank you, Andrea, as always, for supporting this activity, because I have to say that the person behind everything and doing all the practical activity here is Andrea. So big kudos to you, Andrea. Thank you. Thank you.
Thank you very much, Maria. So I will thank again all the participants and Julius, Isaac, Xiao. You did an excellent job. I thank you very much. I thank you very much, Angeli, for organizing this very interesting competition. And of course, Maria, you are the leading voice behind all ITU geospatial GeoAI activities. So I thank you very much, and to the GeoLab for having proposed 2 competitions these years. So I think that we are getting at the end of this event, and thank everyone again, and we hope that we see all of you tomorrow and the next days, also to listen to the other competitions, the final event. Thank you very much again, and have a nice day. Bye.
Thank
A
you.
big applause to
Yeah.
all. Ciao.
Thank you very much.
Thank you.
Thank you.
Bye.
Thank you.
Thank you. Congratulations.
Thank you.
Congratulations, guys. Very well done. Congratulations.
Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.